we have here is something that we call a CSTR, and CSTR stands for a continuous stirred tank reactor. And how a continuous stirred tank reactor works is we have some flow in of material which is reacted in this chamber, and then after which the products are given out. So what we have here is we have some values for a nominal, or rather these are the nominal operating conditions for a continuous stirred tank reactor. So when we take a look at this, we have some flow. We have a flow going in, which is 100 liters per minute. We have this initial concentration of the material going in. We have this initial temperature value here, and we have a few other things that we can use to complete part one, which is to derive the differential balance equations for the concentration and temperature for an exothermic continuous stirred tank reactor. So first things first, let's look at our inflow here. Now at our inflow, we have some initial temperature of the coolant, which is at some initial concentration. Now, as per our little table friend here, we see that our initial temperature here is equal to 350 Kelvin, and our initial concentration is 1 mole per liter. So and the initial flow, or the flow in for this reactor, is 100 liters per minute. Now, within our reactor, we also are given the fact that the volume is 100 liters. So volume equals 100 liters. And now we start focusing on what's coming out of the reactor. We look at the fact that we have this initial coolant temperature, we have this initial concentration of A, and so if we have some initial temperature and some initial concentration, well, we're definitely going to have some final temperature and some final concentration coming out as well. And due to the fact that this is a CSTR, it's a continuously stirred tank, we can go ahead and assume that we're going to have some temperature and some concentration of A inside the tank after it is perfectly stirred, and that is going to be equal to the temperature and concentration of A coming outside of the tank, again, due to the fact that it is a perfectly stirred reaction. Now, the next thing you might notice is that there is some casing for the tank that we have, and this is a cooling jacket that I have drawn out here. So this stuff, that is merely just a cooling jacket. Because, of course, we're referring back to the fact that this is an exothermic CSTR. And so we will be releasing heat in this reaction, and therefore this cooling jacket is just going to cool that down. And so we also have to account for the heat transfer of some way. So let's go heat transfer out of tank. And we can create an equation for it. We'll set the heat transfer equal to T, and that's going to be equal to the total heat here. We denote that with U, times the area, times the difference in the temperatures. Now that we have that, we go back to our drawing board here, and let's list out the rest of our constants. So we have a density. We have a density that is equal to 1,000 grams per liter. We have the specific heat, which is equal to 0.239 joules per gram Kelvin. And we have our heat of reaction, which is equal to 5 times 10 to the fourth joules per mole. And the reason why the negative is on this side and not this side, we are, of course, dealing with an exothermic reaction. So in order to just have a positive heat of reaction to work with here, we're just going to give the negative to this term here and negate that on that side, just so we have something positive to work with. So now we have all of our constants. We've drawn all the information we can out of the initial prompt. We can go ahead, we can start defining our differential equations for concentration and temperature. So first, let's look at the concentration. Now, we have a concentration in, we have a concentration out. So in order to find the differential for that, we want to find the amount of A that's changing over time. And in order to find the amount of A that's changing, we want to use the concentration of A times V. That'll give you the amount of A in the system, capital A. And so from here, we can go ahead, we'll do the differential of that. So dCA times V over dt. However, V is a constant. We just defined that as 100 liters. So we can get rid of that. Bring that out to the front. And we set this equal to the flow times the difference in concentration. And we also need to notice the fact that we have some of A that's being consumed in the reaction tank. So we can define that rate by K, which is the rate constant, times the concentration of A at that specific time, which will give us the units in moles per liter per minute. However, we don't want this liters term here. So what we can go ahead and do in our differential equation, so we want to subtract V times KCA. And that'll give us moles per minute, our rate. So now we can go ahead and divide both sides by V. Which will give us dCA over dt is equal to Q over V times CA minus CAI minus K times CA. And this is the first differential equation we'll be using to solve this problem. So the next thing we want to worry about is the change of energy over time. And that change of energy is going to come from our temperature. So let's grab that. So we are looking for our temperature. However, our temperature is in Kelvin. And we want energy to be in terms of joules. So we could do some multiplications and just do some stoichiometry to try and get this in terms of joules, right? So first thing that we can multiply now is the specific heat. And the specific heat is in terms of joules per gram Kelvin. So there go our Kelvin terms. However, we have joules per gram now. And we don't really want that. So the next thing we multiply by is the density. And density will have units of grams per liter. And so, say goodbye to our grams terms. But now we have joules per liter. So the last thing we want to multiply by is volume. Volume is liters. We cancel out liter terms. And what we are left with is our joules. So we have VPC times T. And if we take the differential of this, I'm going to write this as PVC times T. PVC. With respect to time, we notice that PVC are constants, so we can just bring that out. Rewrite this as PVC times d temperature dt. And now when we look at temperature, there are three things that we have to look at when we talk about changes in heat. We talk about the change between the reactants and the products first. So, oh, that's not what I wanted. So we look at our initial temperature minus our final temperature. That's our change in heat. And this is in Kelvin. This here is in Kelvin. And we want that change in joules per minute. So we'll do the same thing, multiply by C. We're going to multiply by C, which is in units of joules per gram Kelvin. So now we have it in terms of joules per gram. We'll now go ahead, we'll multiply by density. So we'll multiply by grams per liter. These will cancel out. We have joules per liter now. And so to get it into minutes, we want to multiply by liters over minutes, which is the flow rate. So now we have this in terms of joules per minute, which is the flow rate. So we have to multiply by Q rho C. So Q rho C times that, and that's going to give us the difference in heat between our reactants and products. Next, we have to focus on the heat that's being given off by the reaction itself. So we look at our heat of reaction there. So we're going to add this one. And remember why I said we have the negative heat of reaction. So we have this positive. And we want to get this, because this is in terms of joules per mole. We just want to have this in terms of joules. So we need to multiply by the amount of moles that we have. And so we can look at our rate, right? Remember, our rate equals KCA. But that gives us a rate in terms of concentration per unit time. So we want to multiply this by volume to get this in terms of moles per unit time. And so this will also give us our moles per minute. And so these two will cancel out, giving us joules per minute. That's the thing we wanted. And then the last thing is the heat that is being lost thanks to this cooling jacket that we have. And remember, we wrote that out here. So we are going to subtract that heat. So minus UA times T minus temperature of coolant. And now what we want to do, we are going to divide both sides by PVC. I keep calling that P, but it's really rho, so that's incorrect of me, at least. So these cancel out. Our rho and specific heat cancel out. So we are just left with Q. Our volumes cancel out. So we have rho and C on the bottom. And over here, nothing cancels out. So when we rewrite this all out, we get the differential of temperature with respect to time is equal to Q over V times the initial temperature minus the final temperature plus the negative heat of reaction times KCA over rho times C minus the heat loss due to the cooling jacket over rho VC. And that gives us our second differential equation to work with. So the next thing we're going to do for part 2 of this is we're going to go ahead, we're going to use our old friend solve IVP to go ahead and analyze these differential equations that we just derived and look at their behavior over time. So I've already imported the NumPy library, I've already imported solve IVP. So the next thing I'm going to do here is I'm going to open up all the nominal values on my second monitor, and we're just going to start writing these down, right? So for Q, the value for that was 100 liters per minute. So I'm going to write down all the units on the side to make sure that we do the proper conversions where necessary. We're going to go CAI is going to be equal to 1 mole per liter. The initial temperature, TI, is going to be equal to 350 Kelvin. Our volume is 100 liters. Woo. Density, P, yeah, we can use P, is going to be equal to 1,000 grams per liter. Our specific heat is going to equal 0.239 joules per grams K. Our negative HR is going to equal 5E4 joules per mole. Let's see, we have our E over R, which is going to be equal to 8750 Kelvin. We have our initial rate constant, which is equal to 7.2 times 10 to the 10th inverse minutes. Our UA is equal to, looks like it's the same thing as our heat of reaction. So we're just going to set that equal to neg HR. And that is in units of joules per min K. Our coolant temperature at time 0 is equal to 300 Kelvin. Our concentration of A at time 0 is equal to 0.5 moles per liter. And our temperature at time 0 is equal to 350 Kelvin. So now with all these, let me just do something here. With all these units and values in now, let's go ahead. We'll use solve IVP. We're going to define that function and graph out what those differential equations look like. So quick little edit. We are changing that TC, the temperature of the coolant, to 290 instead of the original 300, just because that's part of the prompt and we want to see what happens when we change that from 290 to 305. So let's go ahead and start coding out our right hand side. So we'll just name it that, right hand side. We'll have inputs of T and this vector, and we are going to unpack this vector into the CA and temperature. Ooh. And now we are ready to start looking into the rest of this function. So one thing that we should probably cover is when we look at the rates, we can look at KCA to be equal to CA times the initial rate to the negative ER over T power. And so we're just going to code that into this right now. So we will have KCA, yeah, we'll name this KCA, is equal to CA times K naught to the negative ER over T power. And then we go ahead and, oh, I closed my whiteboard. Oops, 1 minute. We can start coding in our other little differential equations that we have. So we have dCA dt is going to be equal to, let's see, it's going to equal Q over V times CA minus CAI minus KCA minus KCA, and our dt with respect to time is going to be the big long one here. So that's going to be Q over V Ti minus T times Ti minus T plus negative HR times KCA over rho C, neg HR times KCA over rho times C just gonna make sure everything here is nice and bracketed off, and then minus UA T minus TC over PVC. So UA T minus TC over PVC. P times V times C and then we're going to return dCA, dt, and dt, dt. And that should do it for our right-hand side function. Couple little corrections, actually. So this isn't entirely wrong, but I'll just rewrite it. This is times e to the negative e r over t. So we're going to use that np dot exponent. So where is this? So yeah, this will be times np dot exp, and that should have fixed that, and we're just going to return this as an array. So now, let's go ahead, let's solve our IVP. We'll use the RHS function over a time span of 0 to Tn. Let's define that. Tn equals, let's go 10 minutes. Our y is going to be Ca and T. Dense output equals true, true, and method equals reduce. Let's see what I do. DT. Let me take a look at this really quick. Okay, looks like I got her fixed. Everything's outputting. Whoops. Okay, so now let's go ahead. We'll set up our t-plot to be np.linspace from 0 to t-end. And let's go ahead. Oh, get it that way. So now we'll go res.sol over t-end, over t-plot, sorry. And let's go ahead, let's go create some subplots. So let's go ahead and import that library too. So we're gonna go fig equals make subplots. So we'll go fig dot add scatter. We're gonna have our x equals t-plot, our y. For this one, we'll go ahead, we'll do CA. And we will have the name be CA, of course. Mode equals lines. So let's do one thing here. We'll go row here equal 1. And calls equals 2. So this one's going to be row 1, column 1. And we're going to do the same thing. Whoops. I did not mean to do that. Ah, boy. Guess we're going to have to redo that one. Hate it when that happens. Let's see. Mode equals lines. Name equals CA. Row equals 1. Column equals 1. Now, we'll have this one be temperature. This will be in the second column. Let's see. What did I do? I'll come back to this. Of course, I forget to initialize those CANTR. That doesn't look right either. That doesn't look right either. Okay, turns out I had some pretty badly named variables, so I went through, I renamed some of these variables, notably this initial t over here, this initial at times 0, actually, that's what that would mean. And then you go ahead, you use this in your solve IVP, and everything is good and golden. So when we look over here, we see that we don't get to 1, which is the concentration that we have here. So we have 0.5 of this, or we have 5% of the initial concentration that just doesn't react in the system, which kind of makes sense because this is a pretty low coolant temperature. And so the reaction might not go till completion just because there's a lack of heat. We see the same thing on this side. We're starting here and we level out sort of at this 310 Kelvin range, which also makes sense because this is an exothermic reaction. So it's not quite going to hit the temperature of the coolant, but it'll get pretty close. Now let's go ahead. Let's try a temperature like 305. 305. Oh, there's a lot going on now. Let's take this down a little bit. Oh yeah, I also increased the ending time just to get a good picture for us. So now what we see is some oscillatory motion here. Now, we start off with our initial amount. We see that it goes all the way down to 0. And we start rising in concentration, and now we have this oscillatory movement over here. And that lines up pretty perfectly with the temperature. We start at 350 degrees. We have this exothermic, and once this is done reacting, we go down. The coolant starts decreasing the temperature, and we see that this pit here kind of lines up with this peak. So as soon as we start losing the concentration, as soon as the reaction starts going even producing further, we see that our reaction temperature begins to increase as a result. So this oscillatory motion is defined by the fact that we react the material, and once the material is done reacting, the temperature rises over here as the concentration begins to go down. And then once we get to a low concentration over here, that's going to line up with a peak over here. The temperature will start to go down as a concentration of A starts building itself up. So this is the oscillatory relationship in this CSTR reaction.